Morning, everyone. It's my pleasure to introduce our work, use multitask VM for mobile application. The rest of the author on the paper are master student Junyu Chen, faculty member Carl Sigdandu, Steve Cole, and Lucas Derek, all of us from Reliable Mobile System Lab at SUNY Buffalo. In the paper, we look at using multi-app VM. It's also called MVM for short. For Android runtime environment. Before I introduce what is MVM, let's take a look how Android application looks like. Although the hardware configuration has dramatically changed since the last couple of years, but the mobile devices are still resource constrained because the applications are also getting more and more complex and resource intensive. Our observation is that mobile users switch and share data between applications more and more frequently. For example, while we are playing music, we may also use the browser to access internet, and we share our interesting article to the social media application and chat with our friends. When there are multiple applications execute at the same time, they cooperate and they compete on the resource. How Android application handles such of multi-app execution environment. On this slide, shows a runtime architecture of Android application. Each of the app has their own VM instance and runs in separate process. The communication is enabled through the bundle IPC mechanism in the kernel. The bundle communication requires data copy from the kernel, and then it also requires context switch between process. So each of the application runs his private context as like a sandbox. And this kind of sandbox contains application tasks and also runtime components. However, the resource management is typically done in the OS kernel, and it has no information about the applications. Let's see how this affects on the memory management. Each of the garbage collector runs in the application sandbox, and the kernel has his low memory killer that monitoring the application monitoring the memory pressure, and it will kill the process as needed. The problem is that there is no cooperation between the GS in the application layer and the low memory killer in the OS layer. This kind of sandboxed environment is a type of Java runtime. But there are other options like a multitask VM that I introduced in the beginning of my talk. We believe this multitask VM would be a better approach for mobile system. On this slide, the finger shows a default configuration of MVM. Instead of running each of the application separately, multi-VM runs all applications in a single VM instance within the same process, the same memory address. The application isolation is provided through task scheduling and memory bound. The communication is enabled internally in VM, and in the later slides, I will introduce how those details. Additionally, what I want to emphasize here is it has a VM controller that controls the resource request and monitoring the garbage, all of the runtime components. It provides a global view for resource management. And this resource management is one of the major advantages of using multitask VM. The controller has a visibility into all of the applications. It knows the status of each garbage collector and the usage of the resource. It could provide a more holistic decision on resource management. Additionally, running all of those in the application, it also provides fast inter-application communication. The cross-application context switch is cheaper since all of them running in the same process, and then the TLB and the CPU cache won't get flashed. To briefly summarize the difference between single VM and multitask VM. Multitask VM remove process isolation with time and space partitioning, and instead of manage all of those in OS kernel, it provides VM-based resource management. Additionally, it replaces the inter-process communication with intra-process communication, and it only requires a thread-based context switch within the same process. To achieve the isolation I mentioned in the previous slides, it provides time isolation. Each of the tasks of a application are grouped and scheduled as a partition. Each of the partition has their own time slots for execution. VM controller can start, suspend, and resume the execution of his partition. So different partitions can take turn to run in their designated time slots. There are different types of scheduling mechanism in MVM. The application task can schedule directly as OS task. In this mode, it will require less management overhead, but the runtime layer will lose the control over task scheduling. And MVM also provides VM-based scheduling mechanism that run each of the tasks through a thread pool. It will provide finer grained control over task execution, but require a little bit execution overhead. And the designer could combine all of those mechanisms in a partition based on the performance. Also, the space isolation is provided dynamically at runtime through memory bound. This means each of the application cannot allocate object and hold the reference to the others. The VM controller has the information of all of the garbage collector. It can assist VM do a better job for the resource management. For example, here in the slides, it shows 3 partitions. Each of them have their default garbage collector. And if I use the previous example, when the amount of memory is low, VM may not satisfy the allocation from, let's say, partition 3. And at this moment, instead of killing another application from the kernel, what it could do is it could trigger another GC event to the, from another partition and get the memory and then adjust the partition size. By doing so, the system can accommodate as many applications as possible, and also it can make a more holistic view for memory decision, rather than just kill the application from the system. For communication, MVM provides isolation, but it's still a Java runtime environment. So all of the existing Java mechanism are still work. So you can use socket, file, or NIO. At the same time, MVM also provides internal communication constructs. It's more VM specific. It depends on different VM vendor will deliver different techniques for this. The VM that we use is Fiji MVM. It provides shared native variable and communication channel that enable inter-partition non-blocking communication. In this paper, we use shared native variable to measure the communication cost. The preliminary experiment we run is to demonstrate the benefits of MVM architecture. And what we measure is the data sharing between Android and multitask VM. We compare 3 techniques listed on the slide. The first one is Android. It's Android Spender. It requires data copy. So the data is actually copied from sender to the receiver. And the second one is Ashman. The data is stored in the shared memory, and it returns into application as a file descriptor. So the file descriptor will send through the vendor to the application to the receiver. So in this context, it only requires to copy the file descriptor instead of the entire data. For the MVM is similar. Instead of using the OS components, it uses shared memory in VM and send the message identifier to the receiver to share the data. The experiment result that we got here on the slides, it shows the communication cost with increasing data size. The y-axis is the time for communication cost. The x-axis is the data size. The purple line increase linearly is because the bundle requires data copy during the communication. And the blue line and the green line is MVM and Andrew Ashman. The difference is just the context switch between process-based switch and thread-based switch. I know this idea that remove the process isolation sounds a little bit dangerous, even though we have like isolation from the runtime layer. But this concept is not like first brought by us. There are previous literature also share the same concept. For example, Microsoft's Singularity, it also removed the process isolation. It's a research microkernel OS that built with managed language. Both of the Singularity and MVM remove the hard process protection and provide fast inter-application communication. The difference here is Singularity focuses more on static verification and runtime safety. Multitask VM is designed for an alternative mode for Java runtime environment. It tackles application isolation and resource management. Additionally, in order to do the static verification, Singularity provides the in order to do the static verification, Singularity can define his communication with only one sender and receiver. This will increase the development difficulty for the application development. At last, for the drawback, as I mentioned, the application, we remove the application isolation. So what we also lost is also the access control, that we need to provide extra mechanism for the access control at the runtime layer. And a major concern of runtime is native code. Since we claim we can provide isolation, however, the native code will allow a pointer that access any like the data in the memory space. This potential can violate the isolation, and the idea that is we could encapsulate all of the native access. So instead of like the developer randomly access, we expose those as API, and then if the application is required, and then the permission can be granted. This is the same solution that Singularity mentioned in his work. At last, what we are doing now, since the MVM provides an overview for resource management, so it also could makes the system more responsive and predictable. What we are doing is we integrate this architecture into RT-Droid products that enable real-time capability in Android. We're trying to build a mixed criticality environment for medical application. One of the examples is the cochlear implant application. It consists of non-real-time UI and real-time processing components and run with other non-real-time application. And we want to preserve the predictability for the real-time application. To conclude the talk, MVM that we introduce run all application in one VM instance. It provides time and space partitioning. It gives a global view for resource management, and it enables faster communication. That's all.